Okay guys, we're going to take a look at a couple of problems that are projectile problems. I want to take a look at number 29, and then projectiles. That takes you back.
This is long.
But to do this in an efficient manner, you're going to need to actually focus here. Yes, it is.
I'm Ben Butler. I just want to say hi.
As I said, we're going to need to focus. We're going to be looking at number 29, which is a classic kind of projectile problem. If you have your books, page 67. And so what we have in this problem is a football that is launched with an initial speed of 20 meters per second at an angle of 37 degrees. And it is launched from a distance of 36 meters away from a goalpost with uprights that are 3 meters off the ground. And so the question is whether or not the football is going to make it. This is what I call a classic projectile kind of problem. And so there are certain features or patterns that are common to it. The first thing is that we are going to remember that for all projectiles, the acceleration is always 0 in the x direction and negative g in the y direction, because gravity pulls straight down. The second thing is that as we put these quantities into our diagram, we want to label them. The 36 meters that we're talking about is the distance that the football is going to travel here. And that's going to be a delta x. And the 3 meters is the distance, is the height that we would like the football to be at. Let's think about this carefully. If the football is going to make it, then its height has to be what?
Greater than 3 meters.
Exactly. It has to be greater than or equal to 3 meters. So we're going to call this a delta y, but it's really the delta y that we hope for rather than the delta y that it actually is going to be. And then finally, we have our initial velocity. And most projectile problems start with an initial velocity. And what form is this initial velocity given to us in? Polar form, which is the least useful form. We want to get that into rectangular form. And we remember that the x component and the y component are given by what formulas?
The first number cosine.
Yep, x is r cosine.
And the first number sine theta.
And y is r sine theta. Exactly so. So at this time, everybody turn that into rectangular form. Go.
Seniors, if you'd like to come down for the college fair, please do so now.
If you do go down to the college fair, this will be recorded and put on Edline so you won't miss anything much. What do you get for your
15.97 and 12.03?
Yep, I'm going to call that 16 and 12 meters per second. And so all of our projectile problems begin by placing the initial velocity in rectangular form. Having done so, we now immediately move to equations of motion. And we do them separately in the x and in the y direction. In the x direction, I notice that I have the quantity delta x, so it makes sense for me to use the equation delta x equals v0t plus 1/2 at squared. I have an initial velocity. I also have the acceleration. What is the acceleration in the x direction? 0, right. Please, nobody tell me that the acceleration in the x direction is g. Gravity does not pull sideways.
Just for you.
So, 36 meters is my delta x, v0 is 16, and this gives me, and this term is invisible because acceleration is 0. So this gives me an easy solution for time. Everybody find the value of time. Go ahead. Yep. 2.25 seconds. Now here's what this means. If you go back to the football and you imagine watching the videotape of the football doing its thing, what this is saying is that by the time it reaches this point horizontally, the time will be 2.25 seconds. In other words, if I'm watching the videotape of this, the tape counter will read 2.25 seconds when the football crosses the plane here. Now the question is, how high is it? If it's above 3, we win. We get 3 points. If it's below 3, well, the crowd boos and all that. So for that, we go back to the y here. And what we're interested in is how high it is, and that's delta y. And so I'm going to use the velocity in the y direction, which is 12. And I'm going to use the time that we found here because we are looking for the height right at that time, right at that location. And I typically use 10 for the value of g. But if it's close, then I would come back. If it's close, then I'm going to come back and use 9.8. So if I get something like 3.05 or 2.98, then I'll come back and use 9.8 to be sure. Yes?
Why would you use negative 10?
I did. The minus sign right here.
Oh, I see it.
G is the magnitude of the acceleration. Right? So the acceleration due to gravity is negative g.
Yeah.
What do you get? No, no way.
Right, I swear.
I get
45.31.
no, not that either.
Yeah, it's 25.313.
25.313.
What? No way.
Yeah.
25.6458.
Five times.
I get something different.
It's
I get
fine.
1.69,
What?
which is what we got in the other class
How did
also.
what? How does that? Calculator, you big and jerk.
Oh, I was only. Okay, no.
Are you calculating this whole thing?
No, I only calculated the bottom part of it.
I calculated. Oh, I didn't see the top.
No.
Yes, we
That's
have
what
our v0t, and we have our 1/2 at squared, and gravity is pulling down on this thing, right?
Okay. Yeah, that makes more sense.
So 1.69 meters means he fails miserably. 11 meters means it would sail way the heck up over the crowd.
Yeah, well, wait.
And someone would get hit and injured.
Right, something like that.
That makes a little bit more sense.
Okay?
Yeah, that works for me.
Now there are some particular terms that you're going to want to watch out for. Or particular situations that you want to watch out for. One of them is the top of the arc. What is always true of a projectile at the top of its arc?
Its velocity is 0.
That's
In
exciting.
which direction?
Yes.
In which direction?
The
Oh, vertical.
In the vertical direction only, right. In the horizontal direction, it doesn't have any acceleration, right? So it just keeps on making forward progress. So at the top of the arc, the vertical velocity is 0. The second concept is one of range, but I get a lot of students that are real sloppy with their thinking about this. Range is very specific. Range is the delta x when delta y is what value? 0. If you're not talking about a delta y of 0, you're not talking about the range.
What's the range equation?
And the range equation we worked out one day, and that was v0 squared sine of 2 theta all over g. Okay?
I should make sure I got this.
all this is going on. Does that make sense? Okay. Now I want to take a look at a relative velocity problem.
Wait, Mr. Hank,
Sir?
just point out something. Did you mention what I talked to you about the lunch? That one about the problem.
Oh, number 77. Yeah, that's a good point. An issue came up with number 77.
Oh, the one that you were trying to.
On that problem. It's
Yeah.
like fills an entire page. It's just like it's so done.
Yeah. Well, the issue with number 77, we discovered that the answer is in the back of the book is actually wrong because they worked it out with a 20 kilogram instead of a 30 kilogram shopping cart. And so the correct answer, Matt, what did you get?
I got 3.9.
Wait, so
Yeah.
the slide share?
I know.
Is
Well, yes, SlideShare was correct in that it got the right answer, but it used, I'm guessing it was 20 kilograms. It was, if you got the right answer, you had to use 20 kilograms, or use a different value.
Is the 3.9 the actual correct answer with 30 kilograms?
Yes,
Okay, yeah. And then 5.6 was the answer in the back of the book.
5.9.
5.9, yeah.
But yeah,
I want to take a look at a relative velocity problem. And the problem I want to take a look at is number 41. And in the other class, we dorked this one up a little bit, so I want to take special care in feeding for it. We have an airplane that is heading due south at a speed of 600 kilometers per hour. Okay? And now that airplane is going to experience a wind. The wind begins to blow from the southwest at 100 kilometers per hour, which is a significant wind.
what, 50 miles per hour? Sure thing.
Yeah, it's a 60-mile-an-hour gust. And now we're supposed to calculate the velocity of the plane relative to the ground and how far from its intended position it will be after 10 minutes if the pilot takes no corrective action. So the key with these relative velocity problems is how we label each one of these velocities. And you remember that we had a labeling scheme, VAB. And what this meant was the velocity of object A relative to B, the reference frame. And the hard part about this is always figuring out what the reference frame is. And so you want to take as your default the thing that it is traveling in. What is this airplane traveling in?
Air.
The air. That's exactly right. And so we are going to label the airplane's velocity in that manner. The airplane is heading due south at a speed of 600 kilometers per hour. So how am I going to express that velocity?
You put it in, rectangular form?
Yes, I am going to need it, but let's get a labeling first before
Would
we
be
Oh,
airplane wind or air to the ground.
It's the velocity of the plane, but it is not relative to the
The
ground.
velocity relative to the
It's
wind,
relative to the
ground.
ground. That's right.
Wait, so why is it relative to the wind?
Because it is traveling in the wind.
But the speed should be right. So like if you measure your speed like using one of those GPS satellites, it measures your speed relative to the air.
It measures your speed relative to the satellites.
Well, I mean like the number it gives you is relative to the air, not relative.
Is relative to the ground. I think it reconciles it to an Earth reference frame. Yeah, it gives you speed relative to the ground.
But would that not be the same velocity as you're traveling to air?
No, that's because they do the math ahead of time to compensate for all that.
Would it get a different answer?
Yeah, it would. And in fact, we sort of dorked this up, and we took this as VPG at first. and that made our computations complicated and long.
Oh, is it because it's not, you want to be counting an error resistance, is that why?
It has nothing to do with air resistance. It has everything to do with the fact that the plane is actually flying in the air, right?
Yeah, but I just don't understand why that would change the answer. You'd still be going the same velocity.
It changed the signs on some things.
Okay.
So we have the velocity of the plane relative to the wind. Now how do I say due south in rectangular form?
180.
Oh, no.
Rectangular?
Rectangular form.
600 kilometers due south. 600 kilometers-
0, comma 600.
Negative.
Negative 600. There we go.
You're right.
And just to check yourself, you should draw the plane's velocity. There it is, due south with a speed of 600 kilometers per hour. Okay. Now the wind begins to blow, and it is blowing from the southwest. Now that's tricky. If it's blowing from the southwest, which way is it blowing to? The northeast.
That's gonna confuse me.
Well, it is, unless you stop and ask yourself, which way is it blowing? And so, how are we going to label that, the wind blowing?
Don't you have to do
How are we going to label it?
the...
So put it rectangular form.
How are we going to label it?
Oh, velocity of
wind to the ground.
To the ground, that's it. And now we're going to put it into rectangular form. That's going to be 100 cosine, what's this angle here? 45 degrees. 100 cosine 45 degrees, which is 71. And 100 sine 45 degrees, which is 71.
Do you just assume that it's 45? Don't think you do.
Yeah, if it says southwest, you assume that it means exactly southwest.
Will we have a problem where you'll give us something along the lines of southwest?
I'm not going to try to.
You're not going to try to trick us?
No.
Thank you.
If I say something, if I want to specify it in a direction that's not exactly southwest, I would say something like 10 degrees north of west. Or 10, whatever. Okay. And now they ask, the first question is, what is the velocity of the plane relative to the ground? How do I label that, first of all? VPG, velocity of the plane relative to the ground. Now the next question is, how do I compute it? And here is where we do our velocity addition. If you add the velocity in one reference frame to the velocity of that reference frame relative to another one, VPW plus VWG, notice that if it's properly labeled, the inner indices match up, right? Then what you get is VPG right here. And that's going to give us 0, negative 600 plus 7171 equals 71, negative 529 kilometers per hour. Now let's just check that. Let's do a sanity check. If I add this plus this, then according to the numbers here, I get this. Is that a good estimate? Yeah, if I add this plus that, I should get that. That looks pretty good.
Will you have us put it back into a rectangular form?
Into polar form? I could.
Be a jerk.
But if I did, I would not be being a jerk. Simply be being
Being
a
a
teacher.
teacher.
That's right. Now the second question is, how far from its intended position will it be after 10 minutes?
If that thing kilometers per hour, can we use that conversion factor? Conversion factors. I still don't know how we found the same thing.
All right. So what is this question asking anyway?
Change in distance over
Kind of that.
the
Yeah.
change in distance in the x direction after a certain amount of time.
Where'd you get in the X direction from?
It doesn't say that it descends, so it wouldn't the Y position not. The plane's flying straight. It's not going up or down. It's not gaining or losing altitude. So the change.
Altitude would be Z. X and Y correspond to east, west, north, south.
Okay.
Yeah.
But it doesn't say that it's changing direction. Either.
Well, it does, right? So before the wind blows, it's going this way, which is due south.
Yeah.
And after the wind blows, it's going this way.
Yeah. But it
So
doesn't
change
say that
direction.
it doesn't say that the wind lets up. So wouldn't it be flying in the same direction? Like if it's
No, we just calculated.
no,
It's flying that
after the wind blows, while the wind is blowing,
Yes.
is the wind still blowing while the problem's taking
Yes.
taking place?
Yes, it is.
So wouldn't the direction stay the same, 71?
During the problem.
During
Yes.
the problem. So can't we just use what we
So does that mean it's just going to end up at the place that it was intended?
No.
No.
Okay. So the pilot would correct and
So let me ask again, what is this question asking?
What's the delta of what he should be from what he's not?
Good, that's a great way of putting it. What's the delta position of where he should be from where he actually will end up? So, to get that, we're going to need to compute what two things?
Isn't this experience delta?
You just said
Delta and where he's supposed to be,
where he's supposed to be and
where
where he actually ends up, all right?
you have to find the angle he has to correct.
Which one is going to be easier?
Where he's supposed to be.
Where he's supposed to be, because it was due south. So, how would we go about computing that?
you would use 0, -600 after
Uh-huh.
10 minutes to see where he's supposed to be, and then
Tell me how.
You can use conversion factors to
No,
write
you
the
can't.
equation.
Yeah, you can. What equation shall I use?
V squared, no, delta x equals V0 squared. I'm mixing my equations.
Yeah, you are.
Alright, this one out.
Mixing my equations.
I sentenced you to 10 minutes of practice with your equation.
Oh, I'm going to do more than this practice.
All right. And so now we have a velocity of -600.
Wait, did you have an equation sheet?
No.
Do you think?
What's the time that I use? My velocity is 0 -600 kilometers per hour. I'm traveling for 10 minutes.
So do 1/6.
1/6, that's right. 1/6 of an hour. And when you multiply 0 -600 times 1/6 of an hour, what do you end up with?
A 0, 100, -100.
Yeah, that's right. Now we put this on our diagram here. He started here, and the intended position was 100 kilometers due south. That's where he was supposed to be. Where does he actually end up? How do I compute that?
Same way, just use 71
Very good.
525.
Yeah, that's right. So the actual is going to be delta x equals v0t plus 1/2 at squared. Am I going to write the equation a second time?
Yes.
Yes, I am, because I need to practice. And that's -500 and what do we say, 29? Yep. And still, times 1/6 of an hour. And I don't know exactly what you get. Does anybody have numbers on that?
Well, -88.16 per meter.
So 12 -88 is where he actually ends up. That's, going back to our diagram, that's actually like right here. And now what am I trying to compute? What is the problem asking me to compute?
Where he should be at where he is.
Okay,
That.
So
That
that-
looks suspiciously like a triangle.
it does. It looks like suspiciously like a delta x, final minus initial. And so we would say that the delta x is equal to 12, negative 88, minus 0, negative 100, which is 12, comma 12.
So,
Did we answer the question? Not exactly. The question was, how far? What did we find instead? We found a vector quantity, which was his displacement.
polar and take the first one.
Bingo! Put it in polar. Go ahead. Be smart about this.
Is tangent of -1, tangent -1,
Go back to the triangle.
Inverse tangent.
and that's what I meant, yeah, inverse tangent, y over x, plus 180 if x equals 0.
Wait, why are you doing the angle?
Yeah, that's what I want to know. Why are you finding the angle?
Okay,
So just get the r, you just get
square root of x squared plus y squared.
Both of those formulas can be remembered by drawing yourself a triangle. The x and the y are the legs of a right triangle. So the r is the hypotenuse.
It's 16.97, so 20.
Yes,
Or
but
so-
more importantly, it's 12 root 2. Why?
Because that's the more accurate form, because root 2 doesn't.
No. What kind of triangle do I have here?
Right.
45, 90?
That's it. I've got a 45, 45, 90 right triangle, and therefore this guy is 12 root 2, which, as you point out, is 16 point something.
17.
It's
16.95.
So he's 17 kilometers off course after only 10 minutes.
He's kind of bad.
Yeah, kind of.
That's
That's not technically true.
10 miles.
If other players running on autopilot, that pilot would not connect at all.
Yeah.
Yes, but obviously the autopilot is either busted or the pilot's an idiot. One of the two.
They have autopilot, why can you do that?
Because
Because
autopilot is
the
imperfect.
dollars have to fail. Yeah, and like, let's say you have an emergency.
But he's like,
the
there's a
pilot has to
vacuum.
go.
Okay.
John?
Any questions or comments on this? Great. Then that's all, folks.